The reaction of zinc and hydrochloric acid is both a gas-forming and a redox reaction.
Zinc reacts readily with hydrochloric acid, and in this problem we have 10 grams of zinc, and we want to know how much, what volume that is, of 2.50 molar hydrochloric acid is needed to convert that 10 grams of zinc. And the reaction is down here. It's really fun to watch the bubbles. The bubbles are hydrogen gas. Zinc and the H are basically trading places here. They make zinc 2 chloride, which dissolves in water, and hydrogen gas is where the bubbles come from. So no smoking in the lab. Anyway, dumb chemistry joke, but I digress. In this problem, 10 grams of zinc we want to use up, and we want to know the volume of HCl needed to make that go away. So what we're going to do here is use stoichiometry, the relationship between zinc and HCl. So we're going to turn the 10 grams of zinc into moles of zinc, and then the balanced equation says 1 mole of zinc needs 2 moles of HCl. But then, instead of going moles of HCl to grams of HCl, which we did in the last section, we're going to use 2.50 moles of HCl per liter of HCl. And that, if we arrange it right, will give us the volume in liters of HCl, which we can turn into milliliters or whatever. So check this out, it's pretty cool. First, what you want to do is calculate moles of zinc. We're starting with 10 grams of zinc, and to use the balanced chemical reaction, we need it in moles. So 10 grams of zinc divided by 65.39 or so grams of zinc per mole, that's 3 sig figs, 0.153 moles of zinc. Now that we know how many moles of zinc we have, we can use the zinc to HCl relation, which is 2 to 1. 2 moles of HCl are needed per mole of zinc. And if we use that stoichiometric relationship in the 0.153 moles, you can see you multiply 0.153 by 2, 0.306 moles HCl are needed to react with the 0.153 moles of zinc. And then the last part here is that instead of going moles of HCl to grams of HCl, the so-called grams to moles grams dance I was talking about in the last section, now what we're going to do is take moles of HCl and the 2.50 M number. Remember, that means 2.50 moles of HCl per liter. So we'll take that 0.306 moles HCl and divide it by 2.50. And you can see why hopefully we're doing that. The moles will cancel out. We'll end up with a number which is in liters. So we're going to need 0.122 liters, or if you multiply by 1,000, 122 milliliters of 2.50 molar HCl to react with that 10 grams of zinc. Pretty cool. So this is the grams to moles to volume relationship. And if you look in the last section, chapter 4, part 1, there was that grams, moles, grams thing, and I kind of babbled something about, oh, we'll do this in the next section. Well, we're doing it now because molarity is moles per liter. It allows you to go from the moles of a solution into the volume of the solution if you know the molarity, and it's kind of a cool thing. Before we leave this section, we need to talk a little bit about how acids, and as we're going to see in Chem 223 bases as well, how acids and bases are discussed amongst chemists. Acids are very good sources of energy in chemical reactions. And to talk about how powerful they are or how much energy they give, we need to talk about how much acid is there. So the pH scale, which is a little p and a big H, and don't you dare use capital P, little h. It'll drive me crazy. Anyway, you can tell I'm a weird chemist. pH is always little p, capital H. All right, so that's just how this works for some reason. But anyway, pH is literally a way to express how much acid there is. And we'll talk about where this all comes from, but this is kind of the most common groupings of acids and bases. And pHs will go from 0 on the left to 14 on the right. On the left, left, the low numbers, all right, like 0, 1, 2, etc., those are low pH values. And the lower the pH, the more acid there is. So acidic solutions where acids are present will usually have pHs much less than 7. I'll talk about 7 a little bit. On the other hand, 14, most compounds can fall between 0 and 14. Compounds that are closer to 14 have very, very, very low amounts of acid. So low amounts of acid mean that you're going to have a basic solution. So if you have a basic solution, your pHs will be greater than 7. So like we've talked in this section about ammonia, sodium hydroxide, those would have pHs greater than 7. But the acids we've talked about, hydrochloric acid, perchloric acid, acetic acid, whatever, those would all have pHs less than 7. If something has a pH of exactly 7 or close to 7, depending on who you're talking to and what kind of it's referencing, that's when you have what's considered a neutral solution. Blood is pretty close to being neutral. It's 7.4. Usually, it varies a little bit depending on the person and their health and stuff like that. But anyway, normal blood is actually a little bit basic. It's a little bit larger than 7, but that's a very rough thing. Pure water at 25 degrees Celsius should have a pH of 7 as well. But anyway, things that are at least close to 7 are considered neutral. But pHs that are less than 7 are acidic. pHs that are greater than 7 are basic. We have a household cleaner. We test the pH and it comes out to be 9.46. What would you characterize that cleaner as? And it might be a pain in the backside, it's true, but that doesn't count in this discussion. It's definitely not none of the above because we have a pH. So pH 9.46 is greater than 7. That means this is going to be a basic solution. Most things that we eat and drink are actually a little bit acidic, which is kind of interesting. On the other hand, the things we use to clean things around us are usually basic. So like household cleaners and the sodium hydroxides and stuff like that. We'll talk about this more as we go through the course, but it is interesting. However, quickly you can tell if something is acidic or basic. If I said it had a pH of 3.12, you would say it was acidic. On the other hand, if I said pH 10.44, you would say basic, etc., etc. The pH scale was developed by this guy in the lower right-hand corner named Søren Sørensen, and I think scientists just like to write the little O with the line through it. I think it's kind of a cool one. But anyway, he developed this pH scale. P stands for potential. It's the potential of the hydrogen ion. That's apparently what the P stands for. I don't know. Anyway, pH equals minus log H plus. Now let's talk about that. So first of all, pH is the number. 0 to less than 7 is acidic, 7 is neutral, larger than 7 basic, etc., etc. That equals minus log. Log is a base 10 logarithm. And on your calculator, you might have an log button. That's what that is. All right, it's a math function. It's based on powers of 10. It's different than ln, the natural log, but there are ways to translate natural logs to base 10 logs. Don't worry about that. H plus right here, this is that thing in brackets. That's the molarity of the acid. So if you had a 0.1 molar, 0.1 big M HCl, in the brackets right there, you would put 0.1. And that's how they calculate pHs, which is kind of cool. Now, if you truly have a neutral solution, the H plus, which is also equal to the hydroxide, we'll see in a later course, equals this 1.00 times 10 to the minus 7th moles per liter at room temperature, 25 degrees Celsius. So if you wanted to calculate the pH of the H plus here, pH would equal minus log of 1.00 times 10 to the minus 7th. And when you do that, it comes out to be a pH of 7. And I encourage you to do this on your calculator if you have the LOG button. If you don't have the LOG button, there are ways, like I said, to get around it. But this would be a cool thing to know how to do, for example, on problem sets or maybe upcoming midterms. So make sure that somehow you know how to go from an H plus to a pH, which is really kind of cool. If you have an H plus concentration of 1.6 times 10 to the minus 3, you can calculate the pH of that solution. And it's the same kind of thing we just did a second ago. You would take pH equals minus log H plus, and in this case, minus log 1.6 times 10 to the minus 3, pH comes out to be 2.80. And because pH, again, less than 7, that means it's going to be acidic. So again, knowing how to take a concentration to pH using that log function, very important. So make sure you know how to do that. What is the pH of dilute nitric acid with a concentration of 0.030 moles per liter? Now, the nitric acid concentration, 0.030, equals the concentration of H+. So if we wanted to find the pH of this solution, you would go minus log minus log 0.030. And if you throw this in your calculator, it comes out to be 1.52. All right, so again, make sure you know how to do this log kind of thing. It's important to do. If you are having problems with this, please email me and I will have some ways that I can help you get around these problems. I said earlier that most of the things we drink and eat are actually acidic, and that's very true of things like Coke and Diet Coke. So let's say you wanted to test the pH of your Diet Coke. That machine with a little probe sticking in the Diet Coke is called a pH meter, and in a face-to-face class, we would use our versions of pH meters too, which is kind of fun. But anyway, you can see there the answer, 3.12 is the pH. So first of all, if you wanted to know if it's acidic, basic, or neutral, pH is less than 7, so it is acidic. Yes, that's right. The Diet Coke is going to be acidic. Now, how acidic is it? Well, let's figure out the concentration, the moles per liter of the Coke solution. Now, pH equals minus log of H+. So if you put the negative on the other side, you get log H+ equals negative pH. Now, to get rid of that log, you go 10 to the power of, all right? They call it the antilog. 10 to the power of log H+. The 10 power and the log cancel each other out. This is something from math. You do not have to worry about the dynamics. I'm just telling you the kind of ways to get around it. But 10 to the power of cancels log, and log would cancel 10 to the power of. So you have to do it to both sides. So if you go 10 to the power of log H+, you have to go 10 to the power of minus pH. On the left side, the log and the 10 to the power of cancel, so you have just H+, and on the other side, 10 to the minus pH. So if you're curious how much acid, how much H+, or the molarity of H+ is in your Coke, go 10 and little caret, little symbol, looks, you'd go 10 little caret and then negative 3.12, like that. This is the raised to the power of button, all right? On most calculators, some of them are different, but a lot of them it is. Anyway, if you do that, 7.6 times 10 to the minus 4 moles per liter. That's how much acid, how much H+ is running around your Coke solution, which is kind of interesting. We're going to do a lot more with acids, bases, and pH in Chem 223. But for right now, this will at least give you an idea. And it introduces the idea that pH can tell you quickly what an acid or a basic solution is. Chemists don't want to go around and say, well, my solution is 7.6 times 10 to the minus 4. Too many syllables. Chemists are lazy. So if we say our pH is 3.12, instantly you know, okay, that's acidic, less than 7, etc., etc. So it's a very handy thing for chemists to know how to do.